Ampere's circuit law, or ACL. Why are we interested in relating current in a wire to the magnetic field intensity? The reason that we are interested is because it's the foundation for a lot of things, such as inductance, cable heat, and transformers. So it's a good starting point. And it depends on something called the circulation. So just a quick refresher, the circulation is if we have a loop, some kind of circle, like a closed wire, closed path, and inside this path there might be a vector field going through. We want to know how much it contributes to the direction that we go along the path. That's basically what the circulation says. And this is what Ampere's law utilizes. So if I write Ampere's law here, we have that the magnetic field intensity, the integral of the magnetic field intensity along the path of the circulation is equal to the current enclosed inside of that loop. So just for good practice, we'll include the units here. So we have the magnetic field intensity, and that is amps per meter. And then we have the current, and no surprise, the current is in amps. So this is the units. To understand it better, it's a good idea to draw. Well, we can start by drawing the geometry where we have a wire, and this is a special kind of wire. So bear with me, but it's an infinite wire in the Z plus direction, or meaning that it goes on forever, this wire. And then we connect it to a current source, and we have the current running here through the wire. And as we know, when there is a wire through a current, it generates a static magnetic field. So let me draw that. So we have a magnetic field here around the wire. In this magnetic field, we want to measure what is the intensity of this magnetic field. We know that it's related to the current, but how can we define it? Let's first draw a coordinate system. So I'm drawing a coordinate system here where we have the y and the x-axis. And as you can see, this problem is better for cylindrical geometry. So let's define what that means. It means that we have an angle here between y and x, call that phi. And then we have a radial component. Let's call that p. Let's first draw our path of integration. So if we draw our path of integration here, let's draw it more circular, like this. Then we have our radial component p. And p is just, let me just define p. P is just distance from our center. And the radial component is the phi is the angle between the y and x axis, and then we have the z. So these are the things that our geometry depend on. But how can we simplify it? We can make some assumptions about the geometry that makes this problem way easier. One assumption is that since it's infinite, the wire, in the z direction, the magnetic field doesn't really depend on the z axis. It doesn't have any change in the z axis. It's the same along the whole wire. So no matter where we would go here along the wire, you would see the same magnetic field strength. The other thing is that it also doesn't depend on the phi component. And why is that so? That's because if we go around this loop here, then you don't see any change in the geometry either. It's the same from this side to this side. It's symmetrical. So it also doesn't depend, the magnitude also doesn't depend on the phi component. What it does depend on is the radial component, p here. And why is that so? Well, that's because the magnetic field intensity lines here, you see these purple lines, the amount of these lines that we capture when we make this circular blue integral depends on how wide this circular blue integral is. So there is a relation between the magnitude p and the magnetic field intensity because of how much field intensity we capture in this integral. So now we have a good definition of what our integral up here depends on. We can define the differential element because we integrate along a circle, so we only care about the phi element. So let's start by defining that. dl is equal to p times the phi, so the change in phi when we go around the loop. And then we have the unit vector is the phi component here. Another interesting thing is that the magnetic field strength is only dependent in magnitude of p. And why is that so? That's because if there was a radial component and we thought the differential element with the radial component of a H field, it would be 0 because the angle would be 90 degrees tangential. But as we see when we go around this loop here, it's always parallel. The integral that we go around here, the loop and the magnetic field are always parallel. So the angle between them, the cosine, is 0, meaning that the magnetic field intensity is always 1. And this makes the integral much easier to do. So now we can actually define our integral here. If I write it again, we have 0, 2 pi, that's around the loop. And then let me just write it first as we had it before, times the magnetic field strength times the integral path. And then we can insert our now known facts that it only depends on the radial component p, 0 to 2 pi. And then we have our differential element p times d phi, and it's only for the unit vector phi. When we do this integration, it should end up with the enclosed current of the wire. So when we do this, we can relate the current to the magnetic field intensity as the enclosed current over P times 2 times pi is equal to the magnetic field intensity. There's one but, because this equation here only relates the field from the outside of the wire here to P, but when we're inside the wire, the field increases depending on the wire's radius too. So we can define the other integral from the inside of the wire, so let's call this one out and this one in. So inside the wire, the magnetic field is proportional to P times the current enclosed over, so let me just draw what I mean here. So this is the radius of the wire, let's call it alpha, over alpha squared times 2 times pi. So these are the two integrals when we are outside of the wire and when we're inside of the wire. And the highest field is when we are just on the outside of the wire. In this way we can relate the, let me just write final here. In this way we can relate the magnetic field intensity to the current and the geometry, which is kind of neat because then we can determine what kind of magnetic field we would expect around the wire. The limitation of this is that it can only be used for this kind of geometry where there is a lot of symmetrical components. The z direction was infinite and there was no change in the phi direction. This was for a more realistic problem where there was a change in the z direction, it wasn't infinite, or there was a change in the wire, maybe some insulation or sheets around it. It would not be as easy to integrate over. So these are the limitations, and they show up in the differential element dl, as we only integrate over phi in phi direction, and also shows up in the definition of the magnetic field intensity as it's only dependent on our radial component. So this is just the recap.